Welcome back to another video of modern geometry discussion. Topic 1 will be about Hilbert's axioms in real life, from highways to city planning. The following video explores how Hilbert's axioms of incidence and betweenness connect to everyday situations like travel routes, bus stops, GPS navigation, and city road planning, showing how foundational geometry applies to real-world scenarios.
Okay, let's dive into it. We've been asked to discuss Hilbert's axioms of incidence and betweenness. We know these are more precise than Euclid's, but let's make this relatable. Can you think of examples where these axioms come into play in real life?
Sure, let's start with the axiom of incidence. It says that for any two distinct points, there's exactly one line passing through them. Imagine you're driving from point A to point B on a highway. The highway is like the line that connects to the two cities, no matter what route you take. There's one clear path directly connecting the two.
Yeah, I see what you mean. You could compare it to flying between two airports. Airlines have many flight paths, but when you look at it on a map, there's always a single straight line from one city to another. Hilbert's axiom formalizes that, while Euclid's just assume it without proving it.
And this is where the uniqueness of line theorem comes in. Imagine if two airlines claim they had completely different direct flight paths between the same two cities. Impossible, right? There's only one straight flight path, just like there's only one line that can pass through 2 points.
Exactly. And if you think about GPS systems, it's the same idea. You import the destinations and the GPS calculates a direct path. That's a modern day example of the axiom of incidence in action. The device finds a one line connecting your start and end points.
Great point. Now, let's talk about the axiom of betweenness. It describes the order of points on a line. In real life, think about a bus route with multiple stops. If a bus stops at three locations, let's say A, B, and C, and the route is straight, one of those stops will always be between the other two. For example, B could be the stop between A and C.
That's a perfect analogy. The best road represents the line, and each stop represents a point. Hilbert's axiom of betweenness formalizes this order. If you're at stop B, it's always clear that you're between A and C, not some ambiguous point floating in space like Euclid left it.
Right, and this is how we prove the segment construction theorem. If you're planning a trip and you know your two main destinations, the route you're taking is like the line segment. All the bus stops in between are the points within that segment.
That's a good way to think of it. If you know the start and end of your trip, the point along the way are already determined by the order of those stops. This is something Euclid implied but never really improved. Hilbert's axioms let us define this more clearly.
And this connects to how we navigate in the city. Think of walking between two landmarks, a school and a park. For example, the path you take has other points between them, like intersection of crosswalk. The axiom of betweenness helps us understand that any point between the school and park is part of the same segment.
Plus, this gives us the collinearity theorem. If you take 3 points in real life, like three different intersections on a straight street, Hilbert's axiom tells us that one of them is always between the other two. So if you're standing at one of those intersections, you can identify exactly where you are in relation to the other two.
Yes, and it's so practical. It's like standing between two street lights on a straight road. You know for sure that one of the lights is between you and the other, just like how Hilbert's axiom defines the betweenness of points.
And then there's the intersection theorem, which is super relevant when we think about things like roadways. Picture two roads that intersect at a single point, like a crossroad. Hilbert's axiom of incidence tells us that these roads will only intersect at that one point. There's no second intersection unless there's a curve in the road.
That's really useful in city planning, right? When engineers design roads, They need to be sure that if two straight roads cross, they'll only meet at one place. That's exactly what Hilbert's axiom confirms for us mathematically.
Great examples, everyone. So to wrap this up, Hilbert's axioms not only gives us a solid foundation for proving theorems like the uniqueness of line, segment, construction, and collinearity, but they also help us understand real-life situations, whether it's a highway, a GPS route, or a city road. These geometric principles are all around us. Yeah, Hilbert really took what Euclid assumed and filled in the same gap. Now we can not only apply this idea practically but prove them rigorously.
Agreed. Hilbert's formalization might seem theoretical, but it really makes a difference in how we understand and apply geometry in the real world.
So, next time we're out navigating the city or planning a trip, we can think of Hilbert action working behind the scenes, keeping everything in order.
Geometry isn't just abstract, it's practical and foundational to the way we move through and understand our world.
Exactly. Now let's wrap up and prepare for the next topic. Who's up for discussing non-Euclidean geometry next week?
Topic 2 is all about logic over intuition, understanding incidence and betweenness beyond geometry. The following video breaks down how the concepts of incidence and betweenness can be understood through pure logic without geometric intuition, using examples like social networks, schedules, and data organization. The video highlights how Hilbert's approach applies across various fields through formal reasoning alone.
Alright, today we're discussing how the notions of incidence and betweenness can be developed without relying on geometric intuition. Instead, we'll approach this through pure logic and formal reasoning. So, who wants to kick this off?
I can start. Let's take the axiom of incidence. Usually, people think about points and lines in a geometric sense, like dots and straight lines on a piece of paper. But we don't actually need to that imagery. In pure logic, all we need to say is that two objects, which we call points, are connected by exactly one relationship, which we call a line.
Right. Think of it as a set of rules instead of a picture. The axiom of incidence says that if you have two distinct objects, there's exactly one relationship that links them. This could apply to anything. For example, two friends in a social network are connected by exactly one friendship. No need to image a physical line.
That's a good point. We're not talking about dots and lines on a page, but about how abstract entities relate to each other. The relationship, the line, is just a formal connection between two elements in a system. We don't need to see it, we only need to define it logically.
Exactly. This is similar to how computers work. In coding, we can define points as nodes and lines as connections in a database. The system doesn't visualize these points, it simply follows rules to determine the relationship. No need for geometric intuition, it's just logic.
Yes, it's like the internet. Think of websites as points and hyperlinks as the lines connecting them. You don't need to visualize the web, it's just a logical structure where every website can be linked to another, and the connection exists based on the rules of the system. This is incidence without any drawing of lines or shapes.
So true. Now let's move on to the notion of betweenness. In geometry, we usually imagine 3 points on a line with one of them between the other two. But let's strip away that image and think about it purely in terms of order or relationships.
Right. In logical terms, betweenness is simply about ordering three elements. If we have 3 points, say A, B, and C, we're saying that D is between A and C. If the relationship between A and B and C satisfies a specific order, there's no need to picture a straight line, just the logical relationship.
Exactly. It's like organizing events in time. If you have 3 events, wake up eating breakfast and going to school, you can say that eating breakfast is between waking up and going to school. There's no need to picture a timeline. It's just the logical order of events.
Yay, it's the same idea in scheduling when we plan our day. We're not thinking about a line, we're just ordering tasks. Task B is between task A and C because it's happened after A and before C. Betweenness where is just about the structure of the schedule, not a physical space.
And this applies to decision making too. Say you're comparing three choices: buying a laptop, choosing a model, and paying for it. The decision to choose the model is logically between deciding to buy a laptop and actually paying for it. It's all about order, no need to think of it spatially.
Yes, we can even apply this to data analysis. Imagine you're working with numbers in dataset. Betweenness can be defined mathematically as the ordering of values. If I say number B is between A and C, it means B falls within that range. We don't need to imagine the number line, we just follow the logical rule.
And that's what's so powerful about Hilbert's approach. He took these intuitive ideas and formalized them using logic. He removed the need for any visual representation, focusing only on relationships and ordering, which can apply to so many areas, not just geometry.
Yes, and this is how we can prove things rigorously, like the segment construction theorem, without needing to picture a line segment. All we need to know is that given 2 points, there is a well-defined set of elements between them. This logic works whether we're talking about points on a line, events in time, or tasks in a schedule.
Exactly, and this formal logic approach allows us to extend these ideas to things like network theory, where nodes are connected by relationships. We can talk about incidence and betweenness in a way that's purely abstract. No pictures, just rules.
So, to sum it up, when we discuss incidence and betweenness without relying on geometry, we really think talking about abstract relationships and ordering. It's like how we organize tasks, data, or networks. The logic is the same, and we don't need any geometric visuals to understand it.
And that's the beauty of Hilbert's axioms. They work not just in geometry but in any system where relationship and order matter, whether it's scheduling tasks between social network or analyzing data.
Exactly. Hilbert's approach gives us a way to think about these concepts abstractly and rigorously, and that makes them applicable to a wide range of fields beyond just geometry.
So next time we hear about incidents or betweenness, we don't have to imagine lines or shapes. We can think about logic, order, and relationship in any system.
Agreed. It really opens up a whole new way of thinking about mathematical concepts.
Alright, this was a solid discussion. Let's keep thinking about how we can apply formal logic like this in other areas of math. Maybe next time we'll look at how this approach fits with non-Euclidean geometries.